lesson, just put up your hand and then tell us what you are able to learn in the previous lesson. Let's, I can see no one is putting up their hand yet.
Shall we learn about the turning effect of force?
We learned about moment of a force.
Okay, moment of a force. Let's have some control. I'll be selecting people to give us answers such that we have order. And Grace.
Yes, teacher. We learned that the moment depends on the force applied and its perpendicular distance between the turning point and the line of action of the force.
Very awesome. Thank you so much for that. It is a very, very good recap. Yes.
Welcome.
And John Tong and you can submit.
Shall we learn the clockwise and anti-clockwise turns?
What did you learn about those turns?
That they depend on where the object, the mass is put on the, I don't know, the thing they are using.
Those things are names, Tom. You would mention them by names.
I don't know what it's called.
What is the turning point?
Okay, on meter rule, maybe.
What is your turning point? What is the turning point? What is the name where a machine turns?
Fulcrum.
Fulcrum or?
Did they ask you?
Pivot.
Pivot.
Then, so those are pivots or they are fulcrums. Is that clear? Suppose it was a door, what would it be called?
Hinge.
A hinge, good. So those are the things that you are calling things where forces turn about. They are either fulcrums or pivots. Is that okay?
Okay.
Yes, teacher.
Anyone to define for us moment of a force? Someone, may you define for us moment of a force, because it is one of the commonly examined definitions in this topic. Daniela Akelo, unmute and submit.
Moment of a force is a point where the product of the force and the perpendicular, moment of a force is the product of the force and the perpendicular distance from the point to the line of action of the force.
Thank you so much. You've defined it very, very well. Someone else, can you tell us the formula for moment of a force? The formula for moment of a force, Lugolo, we unmute and submit. Someone, you're sharing a white screen, please don't. Thank you.
You said how to
Formula.
find moment.
Formula for moment of a force.
Oh, formula it's the force times the distance.
Force times
Perpendicular
the
distance
distance.
from the pivot.
Yeah, thank you so much. Mr. Gilbert, are you in? Okay, people who are having your microphones open, the noise is so much. Please mute your microphones. Okay, what was the assignment for moment of a force? Bonita, Naranga, S2S, unmute and submit.
The SI unit is Newton meter.
Wonderful, thank you so much. So that brings us to calculations. We went through what moment of a force is. Mr. Sonjove took us through details to understand what we mean by moment of a force, the perpendicular distance and the line of action of the force in the previous lesson. Now we want to go to some calculations in line with that. So I'll share the screen and then we quickly scroll to our first example. Okay, before we proceed, we would maybe get into the factors that affect moment over force. We talked about them last time, okay. All right, now let's, these examples, Mr. Sanjay, we discussed them before we do our first example. May I have someone to just read for us through from moment over force, which we had done last time, and then we go through some examples or applications of these. Someone read for us, Sanyu, Priscilla, and Meet. Yes.
Moment over force is a vector quantity since it has both magnitude and direction. The turning effects of forces are seen in the following actions, or this can be called applications of turning effects of forces. 1, opening or closing a door, window, a lid of a container, for example, a jerry can, and turning of a tap. Secondly, doing or undoing a nut using a spanner. Third, children playing on a seesaw. Fourth, a pair of scissors or garden shears in use. 5, a beam balance being used to find mass of an object. And 6, a screwdriver being used to tighten or loosen a screw. Example 1, a student applies a force of 10 newtons. A student applies a force of 10 newtons to the handle of a door, which is 0.8 meters from the hinges of the door below.
Thank you so much. Okay, let's, you have these notes and the door is there. So we are going to do the moment over force the student applied in order to turn this door. Mr. Sanjay is going to lead us. So the question, I believe someone is saying, what is this? Okay, the force is 10 newtons, Mr. Sanjay. And the door handle of, and the handle of the door is 0.8 meters from the hinges. Yes. The question is find the moment of force.
Calculate the moment of a force.
Right, girls?
Okay, maybe we have someone to work with Mr. Senjove. Okay, someone Otandeka, unmute and submit. Otandeka, unmute and submit.
Yes, so we'll first write the formula, moment of the force, which is F times D.
Use P. For this girl, use P.
P. Raw.
Moment of the force.
Isn't it raw?
Use Mr. Fugonzo, what is the symbol?
Symbol for moment of a force.
Eh?
It has no symbol.
It has.
Momentum is on it has. Okay.
We substitute.
Yes, Otandeka, what are we substituting in F times D?
So the force is 10 newtons. And then the distance is 0.8. I think we can write it as a fraction, 8 out of 10.
No.
The answer will,
okay.
yeah,
The answer.
then the answer will be 8.
8 what?
8 Newton meters.
Thank you so much.
Newton meters.
Wonderful. Let's clap for Tandeka for that very wonderful submission. Okay. Let's go to the next example. Any question on this before we move on? It was a direct question. Just substituting the flag. In case you have a question, you're clapping. Okay. Let's go to the next example. Thank you for that clap, Sanyu. Okay, there's Ntongo. Ntongo, you seem to have a question. Unmute and submit. Ntongo.
Teacher, it's okay. Teacher, it's okay. I've gotten it. It's okay.
Okay, Carissa, unmute and submit.
Some of our notes are totally different. I don't even see that space.
Just summarize somewhere, but the concepts are the same.
Okay.
Yes. Okay, let's go to
So
the
you have
next.
f1y is equal to fxy. What is that?
Diagram.
You have
So you have f1y is equal to f2x. Those things like that.
F1.
What are those?
from these notes or
From the notes we have, the notes we wrote in our books.
oh, okay, the examples are different.
No, you can actually copy the question.
You can copy the question down.
These are the same with the ones we are sharing.
They're not the same. So just copy this question down and learn also this together. Your notes are very okay. It's only that we have different examples. So copy the question and then you work with us. Just use the revision book.
Teacher, please share the diagram.
The diagram, it's just
So
a
we have the
dot,
example, but it's
You don't need the diagram.
and you don't need a diagram, by the way.
Ignore that diagram.
Ignore the diagram.
The diagram was just an illustration, but you can ignore it. We are not snaking. We don't have to be that illustrative. Ignore the diagram, simply copy the question. Those who have different notes, ignore the diagram, simply copy the question, write the solution, and you move on.
Yes, Paula. Paula, unmute and
So
submit.
can you hear me? So
Yes.
can you hear me?
Yes.
So sorry to interrupt the lesson, but I joined a bit late. I'm confused as to what we're doing. Are you going to repeat another example?
Yes.
There is a recording.
Yes, Paula, we are going to go to do several examples, but example one is still on board. We haven't moved far. You can quickly, I know you have it in your notes, and the working is still on a chalkboard, yeah? So try to catch up very fast. The force was 10 newtons. The distance is 0.8 meters. And you know that moment over force is equal to force times distance, which brings us to 10 times 0.8, and you get 8 Newton meters. That's where we are. But also recording will be provided for further clarification.
I think we are done with question one. Can we move to question?
Okay, let's go to question two. Yes, question two. Still, these diagrams are just from a textbook, so you don't have to draw and indicate that dog on a beam balance. I mean, on this beam, or seesaw, you know, on this is actually. Okay, question two. Someone read for us, and then we go through it very fast. Okay, someone is putting up their hand at Kwase Kelly, unmute and submit.
calculate the moment of a force about the fulcrum when a pet dog of mass 10 kilograms is at a distance of 1.2 meters from the fulcrum of a seesaw shown below.
Thank you so much, Kelly.
Okay.
Distance is 1.2 meters. Then the mass is 10 kilograms.
So we don't need mass. What we do?
Okay, so may someone take us through? Someone, you can put up your hand and work with Mr. Senjo on the chalkboard. Okay, someone who hasn't said anything. Nelima, Tracy, unmute and submit. Tracy?
We're going to first find the force, which is m times gravity acceleration.
That has been done.
We are going to find the moment of the force, which is F times the distance. The force, which is 100 newtons, times the distance, which is 1.2.
Which gives us?
Where is my calculator? 100 times 12 out of 10. Then it will be 120.
Thank you so much, Nelima. Now in physics, you don't need that intermediate working. You just use your calculator. You don't have to set 12 out of 10. It's very okay mathematically, but you just use your calculator. Thank you so much. Someone can clap for you. Yes, thank you. Thank you. Any question before we go to the next question? The diagram was just an illustration. We had to convert the weight, like Nelima said, we had to convert the mass to newtons using mg. Yes, unless there's a question, we would love to go to the next. Joanna Sache, any question?
No, check. Okay, I understood my mistake.
Okay, Lugolobi, unmute and submit.
Yes, teacher. Let's say they are given the mass as grams. Do you have to change it to kilograms? Then you multiply, or do you just leave it that way and then you multiply with gravitational?
Yes. Yes, such. What is the SI unit for mass from S1? The SI unit for mass.
Kilograms. Is it kilograms?
Wonderful, right? So in formulas in physics, we always convert to the standard units. So when you're given grams, grams is not the SI unit of mass. It's just the other unit of mass. So you have to convert to kilograms by dividing by, remember that? By dividing by?
1,000.
Okay, someone else can tell us. By dividing by?
1,000.
1,000. So we convert from grams to kilograms by dividing by 1,000. And in this case, the mass was already in standard units, that is a kilogram. Okay, at Kwase Kelly, you seem to have a question and yes, and a message in the chat. May you share with us?
Just to clarify, the acceleration remains 10. Does the acceleration change from 10 or it's constant?
In O level, it's constant. In O level, we use strictly 10.
Especially if you are
especially when you're on the Earth, you go to the moon, the acceleration on the moon is different.
I think it
is equal to 10. It will always be given, stated. Here we are a little bit, because we are dealing with questions, we are not stating it. But under normal circumstances, that gravitational acceleration will always be stated on the question paper.
Okay, thank you, teacher.
Okay, I think we can go to the next question. I don't see any hand. Let's go to the next question. Let me share the notes. Okay, there's an exercise in Longhorn Book 2. You can see it there. So you'll go and try out that exercise. So this brings us the investigation of the principle of moments. So we want to investigate the principle of moments using two masses, and Mr. Sanjay is going to take us through. Investigation of the principle of moments. That's where we are going to Okay, I believe you are in position to see Mr. Senjovi. Tap on that 2-4. I see some hands up. Let's hear from you as you set up this experiment. Letitia, unmute and submit. Letitia.
There you go.
Mr. Bell, mute your microphone. You're disorganizing the lesson. Mr. Bell, mute your microphones. Letitia, you have the floor. Unmute and submit, Letitia.
Teacher, it's okay. It's not.
Okay, Paula Kazina, you're the only person having your hand up. May you unmute.
Excuse me, sir. I just wondered that I personally don't have an book, so
you don't have?
I don't have the book. It's all Longhorn book. So
we shall share some revision questions.
Okay, thank you, sir.
Yes, if you don't have the book, we shall share with you and we shall put in the Google Classroom. Okay, as we are setting up this experiment, any other question or submission? Okay, read through. Let's have someone take us through the procedure as we prepare to do it practically. Yes, Natumanya, you are the first one to put up the hand. Unmute and take us through.
By means of thread teeth, a meter rule is hung so that it balances horizontally with its scale facing upwards. The point where it balances is noted. A 50-gram mass is hung from the 10-centimeter mark. The distance x of the 50-gram mass from T is determined. A 100-gram mass is hung on the other side of the meter ruler. The position of the 100-gram is adjusted until the meter rule balances again horizontally. The distance y of the 100-gram from the thread is determined. The above procedures are repeated when the 50-gram mass is hung at 15 centimeters, 20 centimeters, 25 centimeters, and 30 centimeter marks. The results are filled in a table including values of 50x and 100y shown below.
Okay, so we are going to do that. Observation.
The values in columns 50y and 100x are the same.
Conclusion.
The moments are equal in magnitude but opposite in direction.
Okay, so that's what Mr. Sanjay is going to take us through. I'm going to unshare the notes, so let's focus on the screen such that we see very well.
Before we focus on the screen, it's something I want to just to capture first. Girls, we are going to capture this table of results. Okay? So can you show me the table?
Just take them through. Okay. Let's get the notes back.
First, I want to pick that table. The table of results. The table of results has the following position.
Yes, position of 50-gram mass.
Position of
from the 0
gram mass.
From the 0 mark, centimeter mark.
0 centimeter mark. That one has to be captured. So they have told me it is what? It's 10, 15,
20, 25,
25,
and then 30. So there are not columns of
close. Then the other column,
X in centimeters, another one Y in centimeters,
Y in centimeters,
and then 50X.
50X.
Then we have 100Y.
100Y. That's what you have. Okay. So the first position they're asking us is the balance point. We locate the balance point. So they asked us to find the first position, the balancing point
of the meter rule.
The meter rule. And we note that point. So I'm balancing the meter rule. I hope everybody sees it. So our balancing point, I'm going to take note of. I hope you have seen the meter rule. I can leave it. So that point which I call O, no, it's not O, but the middle point, the set of Mr. Sari, give me that value. It is an estimate.
Okay.
That
is, we can take a theoretical value that is 50 centimeters.
It's around 50. Let us take it to be 50.0 centimeters. That is the balance point or the center of gravity of our meter rule. It is not going to settle there and wait for you forever, people. And that is one of the things that we must learn as we make these observations. Now, they told us to put a 50-gram mass on one side, select a side. We are putting it on this side here. And at how many centimeters? From the diagram, it should be 10 centimeters from one end. So, yeah. And it is measured from the 50 centimeter mark, isn't it? So what will be my distance X?
Someone may tell us the distance X if we put the mass.
Put the center of gravity, and this distance here, X, if they talk about as X, must be the distance between the center of gravity and the 10 centimeter mark. So what distance would that be?
Okay, Namale, Priscilla, and Mutant, tell us. Sorry?
Okay. So can you get us 50 times X and you get us the value straight away?
We want to fill this column 50 times X.
It will be what? The product of 50.
We want to fill this space. So X times 50.
8,000.
2,000. Can someone tell us what is this stands for from what we learned when we get this weight times that distance?
Let us keep that value. We shall convert. Let us, for the purposes which let's maintain that value. Now, girls, I want to do. Should I do step by step or I should do? Let's do step by step.
Step by step.
We need to put that. Okay, now the 100. We are going to balance and find the other one.
So the next procedure will
be placed. I hope you see which direction is this, by the way. Let us release. Let the girls tell us.
Clockwise.
You agree on the direction. We have clocks only.
Digital only.
Those who are like, it is what?
Clockwise.
Clockwise. We must agree that is clockwise. Okay. Now we are going to put the 100 like the experiment tells us and balance. And so this one we are going to shift it.
Yeah. So in this case, we maintain the 50. You maintain the 50, and this one at 10. So
what are you observing? How am I moving the heavier mass? Is it away from the pivot or towards the pivot?
Closer to the pivot.
Closer to the pivot because it is heavier until it balances, okay? So, at 50. So we show what distance. Closer, slightly closer. Closer. Kugenda kusukka. Read the value, read for me.
okay, so it has balanced at 69 point.
So roughly.
Roughly it is 69 point.
69.
69.8. That's what it is. So when you get 50 minus 69.8, we get 19.8.
It's about 19.8. So can you multiply 19.8 by 100? What do you get? Girls, I want you to give me my
1,980.
Okay. We go to the next. That's the value that we have got. We are not shifting values because it's an experiment. We go to the next one.
So the next one
is to 50.
The question said repeat procedure. So you take away this mass and then we shift 10 to 15. You'll do this when you come back. These are some of the experiments to do. So we have now gone to x is equal to 15. And then we maintain the balancing point at 50 and we bring in now this mass on this side. That is the procedure. Practicals are very simple because you repeat the same procedure throughout. So now I want to balance this material again. So it's falling the other side. So I increase the distance this side. Then I increase the moment over force. So it's getting to a balancing point somehow. So we just need to slightly take it the other side, like by 1 mark. So it is at 67.2. Let me put it at 67.3. Just slightly and surely it will balance. Oh, so let's now use 67.2 because it's better than 60. I'm coming. Okay, so it's balancing there, 67.2. Balancing point. So the reading we are going to take out 67.2, that's where. Okay, so y is 50 minus 67 point, it's at 67.1. 6.1 minus 50 to get a distance y. To get a distance y, so it is 67.1 minus 50. So this one was 15 times, if it is at 15, yes, that is 35. So now we need to get this called 50x and 100y. Anyone there with a calculator to work with us?
Sure, 400 is 1,710.
Then for 50, it's 1,750.
1,750.
Okay, so we need to do all these, but this lesson we will stop on this two and then draw a conclusion from there. We are investigating the principle of moments. I want to ask someone, when they are investigating a case, what is the police doing? When they say we are investigating on this case, can someone tell us what does that statement? It is used so much in the criminal world where the police has to look out for criminals. Someone there? Yes,
for clues.
Fingerprint. To look for fingerprints.
Finding clues.
They are finding the source of the issue.
Evidence.
Okay, wonderful evidence. So we want to see that when we talk about the principle of moments, which we are going to state very soon, that the principle of moments, what we are going to find out that the clockwise moments are equal to the anti-clockwise moments. That is a must. That's why this rule balances. It means that this clockwise moment, when I get this weight times the distance, will be equal to this anti-clockwise moment when I get this force times this distance. So in this case, you find these columns. Practically, we cannot get 2,000, 2,000, but the answer is very close because of the practical, the errors in a meter rule. Even we human beings, we are not perfect. So that's why you're seeing that these are not exactly the same, and it is acceptable in practically. Okay, so this brings us to a conclusion that column 50x and 100y, they are the same, and hence moments. So that's what you wanted to do in this experiment, to investigate the principle of moments and then believe that clockwise moments are always equal to anti-clockwise moments. That's what you wanted to do in this, which is shown here. Look at also this is close to each other. The difference comes in from the experimental errors that we do while we are doing the practical. Any question on this before we leave this experiment?
Teacher.
Yes.
Teacher, how do we get the 9? Can you get
Relax.
How do we get the 19.8?
19.8, when you look at the diagram, let me share those notes. We are following the notes in the diagram. Okay, so I want to share the screen just briefly, the screen with that diagram. When you look at x, x was the distance. Okay, let me get my spotlight here. So x is this distance. I believe you're seeing on the screen. The distance, the perpendicular distance between this 50-gram mass and the turning point. So that is our x. So that's why we are getting 50 was put at 15. Okay, the first one was at 10. And therefore, okay, that's about 19.8. 19.8 is a y distance, which is the perpendicular distance from 100 gram, that is the line of action of 100 gram weight, and then the turning point. So that is how we got y. So remember, we determined g in our first procedure, and we got 50 centimeters. So to get y, we see where this is the mass. In that case, it was at 69.8. So there we just subtract the perpendicular distance from the turning point to the line of action, which is 69.8 minus 50. So that's how we got y. Is it now okay? Daphne?
Teacher,
Yes.
no.
Yes, ask.
So where is the zero mark? Is it at the turning point or at the edge?
A meter rule has a zero mark from the beginning. So from 0, it reads up to 100. This meter rule, if I'm to bring it closer to you, it has dimensions from 0 to 100. So 0 mark is this. So we count 15, we put our mass there. Then the turning point was at 50. So that's how we get those readings.
Thank you.
Any other? Yes.
Sure, can you ever be very accurate and get the same distance for 50x and 100y?
It's possible. Those are rare cases, but it's very possible. It calls for a very high degree of perfection.
Because even this ruler may not be very uniform.
Yes, the ruler may not be very uniform, so errors don't only come from the human beings, but also the apparatus we use. Okay, Joy, Banji, Daniela, your hand is up, unmute and submit.
So teacher,
Yes.
I don't understand how you get that.
Excuse me, teacher.
Let's first have one person, but Banji has the microphone. The rest, can you first listen?
So teacher, in the X centimeter column, I don't understand how you get 40 and 35.
40, let me have look at the screen. Are you seeing the screen, the notes? Tap on the notes.
No, teacher, I can't see the screen.
The notes. You touch on the notes.
Okay.
Such that you can come on your screen. Are you seeing my spotlight?
What can you see on your screen?
Sure, nothing.
Because that thing was explained on the screen, and it's what I wanted to do. So you need to tap on the window that has the notes.
The teacher has shared. Tap on Mr. Elsam Senjere.
Mr. Elsam Senjere's window, such that you can see the notes. Daniel, have you seen the screen?
Are you seeing the notes?
Yes, teacher.
So do you see the spotlight?
Yes.
Okay, you were talking about X, how we got X as 40.
Yes, teacher.
In the procedure, they say that the 15 mass, are you seeing this procedure? May you read this line?
50 mass of is hung from the 10 centimeter mark.
So that's 10 centimeter is there, right? That's why we put it practically. Okay?
Yeah, yes.
Then the balancing point, we got it at, do you remember our balancing point we are using in this experiment? What was it?
So I'm not sure.
Okay, when we balance this meter, Mr. Seneko, that is the first procedure. We balance this meter, we can use a thread or a knife edge. So we decided to use a knife edge, okay? So when we balance this meter, it happened to balance at 50 centimeter mark, okay?
Yes.
And then when it balances at that 50 centimeter mark, you note it off as G, okay? So
yes,
in
teacher.
all experiment, you maintain the balancing point at 50, okay?
Yes, teacher.
So this distance X is the perpendicular distance from this line of action to that turning point. That is that distance X. So if this was at 10 in the first procedure and G is 50 centimeter mark, what do you think is the distance between
40.
40? So that's how we got X.
Okay, thank you, teacher.
Any other question? Any other question? Okay. Muto Kimberly, your microphone is open. May you say something?
Teacher, sorry to take you back, but could you please go back to the number before this? Number 2. Are we supposed to change the 10 kilograms to grams?
No.
What are the SI units of mass? Kimberly, what are the SI units of mass?
Kilograms.
So we maintain it as kilograms. We simply convert it to force or weight, which is 10 times 10.
By using that formula, W is equal to mg is 10 times 10.
Your screen is not being seen.
Okay, so I still don't understand.
Not being seen.
Yes,
can see that.
So is your question answered?
No.
Mutonyi?
No, teacher, it's not answered.
Yes.
So we changed the 10 kilograms to newtons.
Yes.
And how do we do that?
We use W is equal to mg. We looked at it in S1 in a topic called forces.
Okay.
W is equal to mg. So we say this mass in kilograms times 10 because acceleration due to gravity is letter g, which is 10. So we multiply by 10 to get 100 newtons.
Okay, thank you.
You're welcome. Any other question about this experiment before we leave it? There are so many hands here. Asimwe, your microphone is open. May you say something?
Teacher, could you explain how you got the numbers in the y centimeter column? Because I didn't understand that.
Okay, you're seeing the notes?
Yes.
Are you seeing my spotlight?
Yes.
So G was at what? What was our G, the balancing point before we put the masses?
Before 50.
50, right? Then Y, the first Y we got was 60. When we put our masses this side, when we put our masses, we add a 50-gram mass this side. So we put it at 10. And then we maintaining this at 50. This at 50, we put 100. We put 100. Yes. You can open the video, it's closed. Okay, so ladies, Asimo, we put in the first experiment, we put 10 at 100, we maintain this at 50, and then we moved. You see how the meter rule is. This is greater, but it has to be balanced, okay? So we moved this closer to balance the meter rule. And then it happened to balance at 69.8. That's where it happened to balance. So when it balanced there, now where we get the 19.8, it's the perpendicular distance. Now introduction talked about the perpendicular distance. The perpendicular distance from the line of action of the mass, where the mass is, we convert it to force, but here we are using this, to the turning point. So you measure off this distance. This
distance is 50.
50.
And this distance is 69.8. So how do you get that distance?
The distance in between. Asimwe?
Yes.
Whoever see that, may God forgive you.
Subtract 69.8.
I am muted.
Okay, so that's how we get the perpendicular distances, and those are the distances X and Y. Any other question on that before we move on? Buyinza Charity.
So please repeat.
Teacher, if we are finding the moments here, why are we multiplying by the 40 centimeters and the 3.5? Can't we just multiply by the 10, or like can't we just like consider the middle point as 0? and then consider the position of the masses. For example,
what is the definition of moment over force? May you remind us? We looked at it last time. What is the definition of moment over force?
Moment over force is the product of the force and the perpendicular distance from the point to the line of action of the force.
So we don't consider any distances. It is that perpendicular distance from the turning point, which called the pivot, the fulcrum, to the line of action of the force. So you don't consider any distance. Is that?
And you don't consider any point. This 50 centimeter mark, we considered it because before we put any of these masses, that is where the ruler was balancing from. That was its center of gravity. So you don't just say, let me now multiply from the end of the ruler, as if that is how I got you. Why don't you just multiply 10 times 40? You don't just guess. We are carrying out an experiment without any mass. The ruler balanced at 50. So that happened to be our center of gravity, and it is fixed. Then the first one was when 50 gram mass was placed 10 centimeters from the zero mark. Then the teachers tried to balance. So this is 10 cent from here to here is 10 centimeters. So when he balanced from this other side, this mass is 100 grams. He kept changing this until when it balanced at 69.8. Now, this distance from here to the center where it balanced from is the x, which we got as 50 minus the 10 here. The remaining distance, and if this is 50 and it is balancing at 69.8, that means the distance now from 50 to 69.8 is 69.8 minus 50. And that happens to be the y, which is in this case 19.8. So while x is 40, y is 19.8. Like you've mentioned, the moment of a force. So on this side where we have 100, you multiply the 100 times the 19.8. That is how we got 1,908. On this other side where we have the 50 gram mass, we multiplied 50 times the perpendicular distance of its line of force, which was 40. And that's how we got 2,000. And the teacher mentioned, ideally we would be getting the same, but practically either the ruler is not uniform or as we balance, we make a mistake. That is why even the wind can blow the ruler and disorganize. That is why the values are not very, okay, they are close, but not the same. Any other questions?
Teacher, also, why don't we change the values, the distance, and also the mass? Why don't we change them like we have been doing to Newton to distance? Yes.
Okay, for the purpose of this experiment, we just wanted you to understand that the clockwise moment is equivalent to the anti-clockwise. But you're right. If we were to be strict, we would change the distance to meters, would also change the grams to kilograms. But have you understood at least the moment?
Yes, thank you, teacher.
Okay, there is Glenna.
Teacher, actually, I'm confused. Where did you get 69.8? Because, yes.
This point where the 100 gram mass is balancing from, when I read it from here, it is 69.8.
Oh, okay.
It's 50. So 69.8 minus 50, then I get the 19.8.
Okay, thank you. I've understood.
You're welcome. Then I can put down your hand and we see whether we have other questions. Mr. Senjowe, there seems to be no questions.
Okay.
I share the screen of the notes.
Okay, let us conclude, girls. What is your conclusion? Suppose we did not have experimental errors, what would be our conclusion? What have you observed about the clockwise moments and the anti-clockwise moments when the body balances on the people? What can you say about them? Ignore us. So my saying is, assume that both these products were the same. What would be your conclusion?
Let me pick, sorry. Namale, I've not heard Namale talking. Namale?
The clockwise moments are equal to the anti-clockwise moments.
The clockwise moments
are equal to?
Anti-clockwise moments.
Anti-clockwise moments. Is that okay? Is there any condition? Is there any condition? Is there any condition?
Jesse Lamaro.
So the moments are equal in magnitude but opposite in direction. So can you hear me? The moments are equal in magnitude but opposite in direction.
What else? Very good. They are equal in magnitude but opposite in direction. Mr. Senjove has asked about the condition. When does that happen? When are the two equal? Anyone, Mr. Kubwan?
Angel Ntong.
So I think the condition is inaccuracy, maybe. And then the two are not equal.
Okay, thank you.
In equilibrium.
When what?
When the body is in equilibrium, just speak.
Thank you very much.
When the body is in equilibrium.
That is the answer.
In equilibrium. Is that okay? So we come up with the
Mr. Some people may be wondering, what do you mean by equilibrium? What do you mean in equilibrium?
Hey.
There are some people use it.
What is it? What does that mean? What is equilibrium? What does that mean?
Imbali.
My colors. These are watercolors, so they are not shouting.
Johanna.
The body is, when the meter rule is balanced.
That is equilibrium.
So equilibrium is when the body is balanced.
When our body is at its state of rest.
And you're working.
It must be balanced.
The colors are not bright, you have to vanish.
People are doing their own concepts. Okay, can we somebody say this?
Let's go.
I have so many.
No wonder it's not able to pronounce.
Okay? How do you like rigid body is acted. Rigid body is acted
Should even be here. Let me get it from the map.
by system of forces.
Let me get
Number of
it.
forces. Number of forces, the sum of the sum of the anti-clockwise moments about a point, in a point, about a point equal to the sum of clockwise moments. About the same point provided.
The body is in equilibrium.
Provided what? I think it's
So the body is in equilibrium.
Is a condition attached.
When a rigid body is acted upon by a number of forces, the sum
And progress when it's about any point is equal to the sum. It's a condition.
when a body is in equilibrium, as long as the body is in equilibrium, that's the condition.
Yeah, that is the condition. When the body is in equilibrium,
For him, it started when there's a body
Under
in
the action of
equilibrium. For you, you
forces,
can
yeah.
end with it.
Okay? While the body is in equilibrium,
Maybe I ask him to read here.
So are we wrapping up, members?
yes, you are wrapping up.
Okay.
So please, you have that statement. I've written it in the reverse maybe, but we are saying that any rigid body acted upon by a system by a number of forces will have its anti-clockwise movements equal to the clockwise movements about any point or about the same point, provided that body is in a state of equilibrium. So that is a very important principle that we always use for our calculations. Okay? For our calculations, we always simply say that the anti-clockwise moments are equal to clockwise moments. But this should not be a statement. The statement should always be that a body that is in equilibrium and acted upon by a system of several forces will have its sum of anti-clockwise moments equal to sum of anti-clockwise moments at the same point. So that principle must always be, try to memorize it the way it is in your notes. And then we shall try to use it in our mathematical concepts when we meet again next time. But at least try to put this.
Excuse me, teacher.
Your head. Yes, please.
Teacher, which are the points? Are they the ones where the masses are?
The turning point. Okay, it is the turning point, but in your calculation, is that point can, okay, it is a turning point. Let's take, whenever you come across that turning point, that's what we call that point. Is that okay? The same point. That pivot or the fulcrum. That is what we refer to as the turning point.
Which may not in all the cases be at the center.
Be at the center.
As we shall see in the examples ahead. Because I think it's time. It's past time actually.
It's past time.
Thank you for your active participation. We shall recap. Yes, we shall have this. Yes, have a nice lunch.
Thank you, teacher. Bye.
Thank you, teacher, for the lesson.
You too, have a
Bye.
nice
God bless you.
Bye.
Bye. God